Today we're going to talk about formulas in the mole. We're going to spend most of our time on the mole because it is an absolutely crucial concept that has to be understood before we can go on in chemistry. And so I want to make sure that we understand this concept in every way. Also, we're going to talk briefly or for some time about formulas. And the chemical formula is the start of actually doing chemistry. Up to this point, we've been talking about things regarding atoms. And now we're going to move on to some things that are a little bit more practical in nature. And so you can get some understanding of how the work of chemistry is done. The fundamental aspect of the mole, I think, is reflected in this quote by John Wesley, which is a fundamental statement that he made about how you can change the world. He said, "Give me 10 men who hate nothing but sin and love nothing but God, and we'll change the world." So let's talk about the various kinds of formulas, chemical formulas that can be written or that can be used to portray things that occur in chemistry. The first of these is just called a formula. The formula is the symbolic representation of elements in a compound. You'll remember we talked about elements. Elements are the simplest pure substances that exist that cannot be separated into other pure substances. And a compound is a pure substance that's made up of elements. And the formula gives you what elements are within a pure substance or a pure compound and the ratio of those elements. So for example, water is a compound that each molecule of water contains 2 hydrogen atoms and 1 oxygen atom. Sodium chloride or table salt is a compound that contains 1 atom of sodium and 1 atom of chlorine. Phosphoric acid is a compound that contains 3 atoms of hydrogen, 1 of phosphorus, and 4 of oxygen. Now you'll notice that these subscripts tell you, and that's the 2, the 3, and the 4 in these various formulas, they tell you the number of atoms that are contained in each of those compounds. Another type of formula is called the molecular formula. A molecular formula is a symbol which tells exactly how many atoms of each element are present in a compound. Now, there's many similarities between these two definitions, but the molecular formula is a subtype of an overall formula. The molecular formula gives you the exact nature of each compound. So you're looking here at the first one is benzene, which has 6 carbon atoms and 6 hydrogen atoms. The second is glucose, which has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Now that's to be distinguished from the next type of formula, which is called the empiric formula. The empiric formula is the simplest ratio of atoms in a compound. Now the 2 examples I give you of empiric formulas are actually the empiric formula for each of the previous molecular formulas. So for example, benzene, C6H6, its molecular formula is C6H6, but its empiric formula is CH. That's the simplest. If you divide both 6's by 6, you get the simplest formula. The second one is the empiric formula for glucose, CH2O. You have C6H12O6 is the molecular formula. The empiric formula is CH2O. And then lastly is a structural formula. Now, a structural formula shows you the spatial connections and arrangements of the atoms in a compound. So, for example, in the diagram above, C is a nice example of the structural formula for methane. What you have above here, by the way, are the simple formula for methane a stick formula for methane, a spatial formula for methane, and then what's called a space-filling formula for methane. All of these are the same, and we actually have some examples on the next page here. This is a molecule of sulfur. Molecular sulfur comes with 8 sulfur atoms in it, and it can be represented either by a structural formula, which is shown in A, a ball and stick model, which is shown in B, or a space-filling model, which is shown in C. In these cases, the yellow is frequently used to represent sulfur, and that's because sulfur is a yellow substance in real life. Now here's the same representation of benzene. Benzene, as I said before, is C6H6. So the first is the structural formula, and it shows you that not only are these arranged in a certain way, but they're arranged in a ring. And in that ring are 3 double bonds represented by the 3 double hashes here and here and here. And we'll talk a bit about this kind of bonding in a future lecture. And then, so these carbons form a ring, and then around the outside are the hydrogens. And this is the structural formula for benzene. And here's the same formula in a ball and stick structure. And again, what you see here is the double bonds interspersed with the single bonds in a ring formation with the smaller hydrogen atoms on the outside. And here is the space-filling model. Now, it's difficult to show single versus double bonds in a space-filling model because the spaces are filled and you can't see the actual bonds. And then lastly, this shows you what benzene actually looks like in real life. It's a clear liquid in this bottle. Now, the second concept when we think about formulas or something is something known as an isomer. And an isomer, by definition, is 2 compounds. Isomers, by definition, are 2 compounds that have the same molecular formula. Okay, so they're the same molecule in terms of what atoms are in the molecule, but they're different in terms of their structure. And because of this difference, you end up with a situation where they do not necessarily act the same chemically. They're not necessarily the same compound chemically. So isomers frequently are very different from each other in terms of their character. Okay? So if you start with the general term isomer, you have 2 major kinds of isomers. There's the constitutional isomers, which are structurally different, and then the stereoisomers, which are spatially different. In other words, the way they're arranged in space is different. So constitutional isomers are situations where the atoms are not in the same place. Here you have 2 compounds which has exactly the same molecular formula, C3H7F. But you notice this one has the F on the end carbon. This one has the F on the middle carbon. Now, if this F were on this carbon, it would still be the same compound because it would just roll over. But when it's here, it's different. Now, these 2 will have different chemical properties, different names. There'll be ways of identifying these 2 compounds. So these are constitutionally different, structurally different. Now, here we have spatial differences, and there's actually 2 kinds of spatial differences. There's something known as diastomers and enantiomers. Now, the enantiomer is represented here with these, and what you have is a right-handed and a left-handed molecule. In other words, if you look, in this case, the chlorine is spatial and fluorine is spatially arranged to the right. And in this, the chlorine and fluorine is spatially arranged to the left. And the solid triangle means that the chlorine is coming out of the screen towards you. And the dashed triangle means that the fluorine is going into the screen. These 2 are in the plane of the screen. So if you were to look at it, it's like three legs of a tripod with the hydrogen sticking up. These are all in the same plane. This is coming out towards you. This is going into the board. Now this is coming out towards you and going into the board in the same way, but it's on the left. One is on the right side, one is on the left side. And so these two are different. Now the most significant biological compound that's like this are amino acids. All amino acids have a left-handed and a right-handed version. And as it turns out, the ones that make up the proteins that are in our body are virtually 100% right-handed. Now, over here, what you have is a spatial difference, but instead of right and left, it's called cis and trans, which means in this one, you can see that both of these CH3s are on the same side of the chemical bond. Thus it's called cis, meaning same. And this, the CH3s are on the opposite side relative to this double bond. Therefore, they're across from each other, and they're called trans. And that's the difference in this sort of diastemer. The other way the diastemers can be different is in a rotational sense. You see here you have a compound like benzene, for example. You have two CH3s substituting for two of the hydrogens in benzene. Here they're close together, and here they're across from each other. And there's also a third one that can be here and here. Those are called conformers or rotamers. So here are all the various ways that these can be spatially arranged. And all of these are different examples of different kinds of isomers. In a very small way, we will be talking about this probably in the fourth quarter when we talk about organic chemistry, because most of these differences show up in carbon chemistry and in organic chemistry. So, like this is a organic compound here, and these two are organic compounds as well. And so these kinds of differences we probably won't be dealing with, but I want to introduce the concept to you at this point. So structural isomers are isomers which are different, have different connections of the same atoms. And here we have a different connection for the fluorine here and here. Whereas spatial isomers have the same connections, but they're oriented differently in space. And there's all kinds of examples that we've just gone over and how that can occur.